Good afternoon, and welcome to the fourth edition of our summer lecture program here at Berkeley Lab. Thanks for coming. So for today, we're going to be talking about light. And to introduce our speaker, I'd like to bring up Alan Chen, who is from the Communications Office in Environmental Energy Technologies. Alan?
Thank you, Ron. Well, hello, everyone. I'm very, very pleased to be able to introduce Dr. Michael Siminovittch, with whom I have worked for several years now, writing articles and press releases about the technology that he develops in his laboratory for more energy efficient lighting. I'm going to start by saying that Dr. Siminovittch and his coworkers may already be a part of your life. You may or may not know that, but if you work here at the lab, you may have a Berkeley Lamp on your desk, and that came out of his lab. If you happen to have at home a Torchiere like this that uses a compact fluorescent lamp instead of a halogen, then his technology is already part of your life as well, and he's going to be talking more about both of these to you this afternoon. Dr. Siminovittch did his undergraduate work at Carleton University in Canada, and graduate work at the University of Illinois. He has a master's degree in architecture with a concentration in energy efficiency, and a master's degree in industrial design. And he completed his doctorate at the University of Michigan, concentrating on human factors engineering in industrial work environments. He is the manager of the Energy Efficient Lighting Fixtures Laboratory, which he's going to talk to you about more. It concentrates on developing lighting technology for the residential, commercial, and hospitality segments of the economy. He has more than 40 technical papers, 5 patents, and a couple of patents pending. And he asked me to mention 3 things to you before he starts that I think will frame his talk very well, which are these points. That his laboratory focuses on developing energy-efficient technologies and getting them from the lab into the marketplace. The work, unlike some of the pure research that goes on here at Berkeley Lab, their work is not done until this energy-efficient technology is adopted in the marketplace. And in order to do that, they work very closely with the lighting industry. They have a close and continual relationship with the lighting industry that helps ensure that the technology coming out of his laboratory actually is useful. And finally, he wanted me to emphasize that the work that they do is a team effort. And one of his team members is here in the audience today helping out. And I hope you will all join me in welcoming Dr. Michael Siminovittch.
Okay, thank you. Thanks, Alan. Well, thanks very much for the introduction. Yeah, I just turned it on. And thanks for all coming. I'm going to talk a little bit about some of the work that we're doing at the Lighting Systems Research Group. And I essentially wanted to focus on most of the activities that we work on with technology transfer and with brokering partnerships with industry, ultimately leading to commercialization of the research and development work that we do here at the lab. First of all, lighting is a real significant part of our life. It impacts the quality of our work environment and the quality of our home environment in terms of the luminous distribution inside our spaces. It's also very important in terms of energy efficiency, and it makes up a fairly large section of energy use in this country. One of the areas where we really concentrate on is trying to identify areas where we as engineers and scientists can be effectual in making change happen. And in the lighting efficiency arena, we've identified by working through partnerships with manufacturers and end users, we can actually make a difference and commercialize these technologies. Energy savings in lighting is sort of been a long-term interest of ours, and there's lots of different ways to go about this. Obviously, in a 100% daylit space like this, you don't rely on any electric lighting at all to light the space. So ultimately, this is a very efficient environment. many factors to consider in these kinds of applications. One is that the daylight inside this space creates a lot of potential glare and can impact the quality of our life and our productivity in our work environment. So these types of energy efficiency measures need to be very carefully considered as we implement them. Traditionally, in the energy efficiency process, we've looked traditionally at source efficacy. And source efficacy is lumens per watt. How much light do we get for the amount of power that we put in? And a lot of research and development effort taking incandescent sources and evolving inherently more efficacious light sources. And we do a lot of work at the lighting group in this arena. Also, we do a lot of work in lighting controls. And again, the energy use is a function of power and time, and the critical element there being time. If we can limit the amount of time that a light source is on, we can generate a lot of energy efficiency. And on a simplistic basis, that's just turning your lights off if they're not being used. Thirdly is the whole arena of light distribution. And light distribution refers to how do you take the light that is produced from a lamp and distribute it in a work environment? And how do you do that effectively, both for energy efficiency, but also for quality of life? The distribution of light at your work plane is very critical in terms of your visibility and your comfort. This is a task lighting geometry that we evolved for the United States Post Office for letter sorting facilities, and it's now forming the standard for all letter sorting facilities in the country. And we spent a lot of time looking at energy efficiency, but even more time looking at how could we create a task lighting geometry that would positively enhance his environment for sorting mail and create high levels of contrast and luminous comfort. So what I'm going to talk about is the bridge between the development of new technologies in the laboratory and the demonstration functions, but ultimately brokering partnerships with manufacturers, utilities, and end users to take that technology into the marketplace. And that's really what I mean by being effectual. It's the things that we can do here at the laboratory to make a difference in that process. You're all familiar with these fire on a stick torchieres, okay? Many of us have these things at home. Very popular lighting system. And at one point in time, a number of years ago, it was one of the largest selling fixture types in the United States. About 15 to 20 million of these things. Very popular, but a lot of power. About 300 watts per system. So it was a very significant problem in terms of both energy use and fire safety. And we got very involved in this very early on this process. This is a close-up view of this, and this is essentially a filament that glows, and it glows at a very high temperature, and it happens to produce a little bit of light. And the issue here is that it's inherently very, very low efficacy in the 10 lumens per watt region. So at this point, we got very interested in saying, what could we do about this very, very popular fixture type in terms of advancing some new technologies? At the time we started working on this, universities across the country were starting to get very concerned about the safety issue on this. Most dormitories in the United States, the students would use torchieres to light their tasks in the dorm. And so the university management was starting to get very concerned about the fire safety issue and started to implement selectively some bans on the technology. In other words, you cannot use a halogen technology in the dorm room. We got called in by the consumer product safety people, and they said, look, we're very concerned about this technology. And at that point, we started collaborating with the manufacturers across the country to say, look, what could we do as a development laboratory to address this issue? So it was both a safety issue, a manufacturing issue, and in our minds, very much of an energy issue. This is some infrared thermography work we were doing, in which we would take a torchiere and we put it on a wall, and we would look at the heat generation from these things. And the big issue here was fire safety. This 300 watt torchiere produces a lot of heat, very high temperature, and the fire safety issue was very critical. We got very involved of taking some next generation light sources, and these are essentially next step compact fluorescent. These are very high output, very small, very high quality phosphors, not your old fluorescent, but very high performance, high quality. And lamps that generally were not being used. And what we did is we worked with the lamp companies to help evolve this technology specifically for torchieres. And so we got very involved in the laboratory looking at a lot of optics work, looking at a lot of how could we make this technology work in a consumer product that would produce the right amount of light, but do it a lot more efficiently, a lot less heat, a lot less of a safety problem. This is one of our earlier torchieres that ultimately led to the first torchiere, which is this one here, which you can, it shows the compact fluorescent lamp in it. This is, whoop, Eric, can you grab that? You can go into Home Depot and actually purchase that. So we worked very closely with the lamp manufacturer on this, and then ultimately got it out to the fixture industry. Worked with a wide variety of different types of high-performance lamps, and these are lamps that are in the 60 to 70 lumens per watt as opposed to the 10 lumens per watt that you see with the halogen technology. So a big step forward with very good color performance and very good longevity. So in the early processes of this technology development, it was mostly a laboratory effort in which we were able to show optically and electrically and photometrically that these technology worked well in terms of matching the performance of a traditional halogen technology. Just a little bit of cross-compare here. A typical halogen technology uses about 300 watts. The systems that we were working on in the laboratory were using 30 to 70. So it was a big step down in terms of the amount of power with about the same amount of light. If you look at annual energy costs, if you own a halogen technology, it can be very expensive. A typical Torchiere, a lot less, about $55. Big factor here was that the operating temperature of a typical Torchiere you see at home is about 700 degrees. If you put anything on there that's combustible, you will have a fire. The compact fluorescent technology is in the 140 degree region, and if I put my hand on this, it's warm. If I put my hand on a halogen Torchiere, you have a nasty burn. So what we did early is we took this technology out to the marketplace, and again, through our contacts and partnerships with the lamp manufacturers and with the fixture manufacturers, we're able to get them interested initially on this as a future alternative. And so based on some of our early activity, we've got about 5 or 6 manufacturers to actually commercialize this. The process initially was very, very slow. And the reason was that they said, look, we're selling an awful lot of halogen technology today. Why should we even bother with your more expensive compact fluorescent technology? So went back to the drawing board a little bit. And at this point in time, we were constantly being approached by universities. And Stanford University approached us and said, we have a massive problem down at our university where when the students come home from class, we can tell because the needle on our utility meter pegs out. Because when everyone's turning on their 300-watt Torchiere, it was one of the largest plug loads on campus was the Torchiere. So they were very concerned about this. They're also very concerned about the safety issue. So we worked with the director of housing at Stanford and their energy folks, and we developed the concept of doing a fairly large, very high visibility swap out program where the students would come in and they would bring in their old energy efficient technology and they would get a brand new efficient one. And the idea at this point in time was by creating this type of event and demand for this, we were able to go back to the manufacturer and say, hey, this is real now. You've got a Stanford University and a major utility saying, let's play. And at that point, that helped solidify the interest as a commercial interest. So the Stanford event was very critical for us. This is some shots of the actual swap out program, and here's the dorms lined with Torchieres. And this swap out event, we did 2 high-profile dorms down at Stanford, and every one of the Torchieres we were replacing. 90% of the dorm rooms had 1 or more 300-watt Torchieres. So this was a fairly massive program. And we did a lot of work on looking at the quality of this light source inside dorms, and we did a lot of photometry, and the Torchiere that we used in that worked very well, and students were very happy with it. We filled up lots of garbage bins with old Torchieres, and this was a big event on campus. And it was well televised, and we got a lot of other universities as a function of this to do this. There was Rice, Brown, Harvard, lots of other universities did this, and it formed the backbone of the California programs for all the utilities. All the utilities now are doing swap out, or have done swap out programs based on this early program that we evolved here. We partnered with a number of different utilities, and we did programs with residential, which we took our technology with the manufacturers, and we did a before and after. And what we're showing here is basically is a monitoring of time of day, in which this is early in the morning, and you see there's actually people using the Torchiere, but very heavy usage in the evening. And then we went into a whole series of homes where they swapped out, and we did an after. You can see very significant savings. This was a really good project for us, and it got a lot of high visibility, and we were able to get sort of the technology into the marketplace quickly based on this visibility. We got the Popular Science Grand Prize for Best New Home Technology on this, and this really helped seed the market, and where people got a lot of interest in this, and there was a lot of press. And so the rest of the manufacturers came in, and there's now a number of these producing this. We also got the opportunity to meet senior management, and for those who don't know, this is Secretary Pena, the previous Secretary of Energy. This is the Director of Housing at Stanford. This is the president of the company that produced one of the Torchieres, and that's me wearing a tie, and it's the only picture that exists of me wearing a tie. And my boss said, "You're not going unless you're wearing a tie." So it was a compromise. He said, "Not a black tie either." So, based on a lot of this work, we started to understand that by brokering these types of end-use partnerships with manufacturers, we could sort of accelerate technology into the marketplace. And the Berkeley Lamp was sort of reflective of, again, this process with a little bit more formalization in it. And what we did is we formed a laboratory utility state partnership where everybody brought something to the table to help get this technology into the marketplace. And we evolved this high-tech table lamp basically as a high-performance task light which would enhance visibility in a traditional work environment. And the idea was the Trojan horse on this was going to be lighting quality and amenity. How do we reduce screen glare for people who work many hours behind a computer? How do we put control features in there that people want to use to be able to change their light? We know if you have control over your lighting system, you're going to be much happier with it, and it's going to create higher levels of visibility. We know that. So we tried to bundle all that technology together into this lamp, with the last process being energy efficiency. What we did is we borrowed very heavily from our Torchiere. This was the commercialized GE Torchiere, and since we developed that here, we had a problem taking the same technology, and we put that into the Berkeley Lamp. And the Berkeley Lamp, the essential features of this is that it's a lot of light in a small package, but it offers you unique distribution characteristics you don't normally get with a table lamp. Table lamp here can be used in a 100% downlight mode, 100% uplight mode, or in a combination. And plus it's got a ton of light. This is actually one of the lamps here turned down low, but it's got two of these high performance compact fluorescent lamps. And you can see I'm relatively pale, but my hand is very well rendered. So it's a very high color quality. And this is a new type of phosphor that they're using on this. So this was the prototype that we developed that essentially does this unique optic that makes it work very well on a task plane. And most of the studies that we've done, high levels of user preference in traditional office environments. This lamp works very well as an indirect lighting system for people that are doing complex VDT tasks. Like this person's doing a lot of CAD modeling. And the unique feature here is that when you're sitting at a computer terminal doing this, you don't want flux reflecting onto the screen from your light source into your eye. What that does is it reduces contrast. And at the end of the day, your eyes are tired, and you said, well, I worked really hard. It's probably because of your challenged lighting system. With this type of indirect, you can turn all the light on this so that it goes upwards as a Torchiere. And we know that indirect lighting systems are the best lighting system to have if you want to render a screen very well. Also, this gentleman's presented with a lot of complex paper tasks all day long. And it's very good for that type of environment as well. It creates a lot of flux down. So the lamp has a multiplicity of functions that it can do. Here we're trying to capture the whole concept of very low screen glare. In this type of environment, you want to have good luminance on your keyboard, good luminance on your surround, and you want to have a screen that's virtually unlit. That's the best lighting environment. Folks that work on VDTs or computers in the dark are really doing themselves a disservice because you go through transient adaptation problems. As you focus on your screen to the dark, your pupil oscillates. It opens and closes, and this renders fatigue. With this type of geometry, the task plane and the keyboard are well illuminated, but there's hardly any flux directed towards the screen. It creates very high levels of screen glare, very low levels of screen glare. The energy efficiency process on this, again, this is a two-edged sword. One is that we get high levels of visual quality, and when people put this on their desk, they can reduce or eliminate the overhead lighting. There's not a lot of folks who are overly impressed with fluorescent lighting that's on the ceiling. There's not a lot of folks I know said, oh, I really like my fluorescent light sources on the ceiling. Okay? So with this type of environment, what we have found in the many test sites that we have is that people, without being asked, will turn off their overhead lights in preference to this. And this is where we get the energy efficiency. And we're getting about 50% energy savings pretty much wherever we go with this kind of thing, with a fairly strong preference for the light source. I'm trying to capture that here where we're showing before and after, where in this environment here we have these three fixtures and now we only have this one. It's kind of hard to take a picture of lighting systems, but that's an attempt to capture that. What we did is when we found out all this information about the energy use and about the high visual quality is that our interest was to get this technology out into the marketplace. So we formed a consortium of the three utilities in the state, Sacramento, Los Angeles, and San Francisco, PG&E. And we put together a program where the utilities agreed to buy the first production based on the LBL design. And so what we did was a national solicitation, and we went out to the world and we said, please build the Berkeley Lamp. And we did it competitively with a very strict sense of specifications, and we worked in it as a partnership supporting the utilities to go do this. Based on this, we were able to evolve a license with a manufacturer and a technology transfer process, and we were able to commercialize this with the three utilities. The lab showed lots of leadership. This was the retired facilities director, and he put this lamp in all kinds of different places. We've had real issues with the lamp in terms of the ballast, and that is this component here. And the lamp is being reintroduced this month with a new ballast, so we won't be suffering any more of the ballast failures. We had a lot of ballast failures on this, and this is the kind of process you learn from in market transformation or commercialization process. With anything new, there's bound to be failures, and we had a lot of failures on the ballast. So we found that people really, really liked the lamp, but they got really ticked off when it failed. So growth experience. This is Eric, my partner, and we deployed this out at 3 different national parks. I've relit their offices with this, Death Valley, Yosemite, and Fort Mason. It was interesting. Death Valley, as you can imagine, is a relatively warm place. And they were real interested in this because they were able to displace a lot of the overhead lighting. And it turned out that it was the equivalent of a heater in every single space. So they were very happy that they were essentially taking a heater out of every one of their rooms, the equivalent of doing that. So this is a picture over at the park over at Golden Gate where they've relit their executive offices with this. And again, the staff there really likes the lighting quality. And you can imagine these overhead fixtures here created enormous amounts of screen glare. Most overhead lighting is not designed to work well with computers. This kind of technology came from the 50s. Okay? This technology is not a 50s technology. Okay? So these things are relatively incompatible. The lamp actually works very well in VDT environments. This is a program we did with the VA hospital, and we're finding that this works well in small offices as well as large offices. And in this environment here, again, the driving factor on this is the relatively low screen glare on this thing, and the idea that this person has direct use over it. So very high levels of user preference. Again, we have to hang our hats on energy efficiency. We can talk about lighting quality all day long, but the folks at DOE want to hear something on an energy story. And this is some of the data that we're getting back from the field where we're tracking energy use over a day. And this is data that's been averaged over a long period of time for a series of offices. And what we're showing here is morning through to fairly late over a very long period of time. And the blue bar here shows an average for the conventional lighting system in a small office environment, averaged over many, many, many days. And you can see this person in this room typically gets in at 8 o'clock, but sometimes he works there fairly late. You can see there's a fairly, this person's here to late at night. And after, we put a Berkeley lamp inside these offices and monitor the same thing. Again, the person gets in reasonably early, stays, still late hours, but we're getting more than 50% energy savings in this environment with the coincidence of high user acceptance. Same thing as we did a big deployment down at the city of Berkeley in the engineering offices, and these were folks we were real interested in working with because they were very demanding and they had very high visual quality needs, and they had no problem giving us feedback, which is always important in this kind of process. And this is a before and after, and we're showing, again, time of day along this axis, and this is before, showing the average power. And this is a relatively large office. This is about 11 people. And again, we relit the whole office with this. And showing the sort of the step function, then it's on all day, and then it's gone. And with the after, we're getting about 50% savings, again, with the same technology. Just about pretty much any office we put this into, we get about 50%. We also are starting to look at teaming this up with occupancy sensors. And occupancy sensors are technology, again, it's energy is power times time. And this is a little plug strip where you can plug something into it, and then there's a little occupancy sensor here, which, as a function of if you're there or not, it will turn whatever technology is plugged into this. And plug loads are big users inside offices. Lots of people have electric staplers, fans, aquarium motors, all kinds of stuff, stereo equipment. And so the idea of being able to control that with a sensor, that if this doesn't see you, it will turn whatever's off on that strip. So we got really interested in doing some of these deployments, and we did a big deployment at the Air Force Base where we put all the Berkeley lamps in with one of these. And we studied this a little bit. What was interesting was this is 3 days of data. And what we're showing here is the person arriving in the morning, the lamp gets turned on, and we have a little monitor in there that measures the light's on or not. Now, this is no occupancy sensor. The light is on, and it's on for a whole 8-hour period. Person leaves, they turn off the lamp, and they're home. And it's off all night long, and then it's next day. So these are 3 discrete days without any lighting controls at all. Same office space. What we did is we came back in, we put an occupancy sensor in. And this is what we got. Person comes in the morning, turns their light on. They split to go out for a smoke or whichever, back in, and then they're out at noon, and it looks like they goofed off all afternoon. Okay? And this is actually the cleaning person coming in. And they're not turning, this is all automatic. When you walk in, the lamp comes on, bang, it comes on. So this is the cleaning person. Okay? But you can see that, and we have lots of this data, so we really know when people are there or not. It's kind of interesting. Anyway, so the next day, same thing. They come in the morning, they split for lunch, they come back. Now they have to make up for all the time they lost the other day, so they spend a really good afternoon there. But what's interesting here is you get about a 30% savings, and this is just a standard office task. So it shows you that it doesn't matter how efficient a light source is, if it's on, you're not saving anything if there's nobody there. So the idea is that we want to start integrating these kinds of control systems inside these spaces. We did lots of surveys on this technology, trying to understand what people liked and didn't like, and this can get fairly intensive, but this is just a boil down of one building we did. And it turns out that most folks really like this lamp on their desk. And outside of the lamp failures that we've had because of the quality control and the ballast, separate from that, there's been very high levels of user preference on this. Most people were pretty happy with it. We did get one or two people in large groups that say, I don't like it, I don't want it. And that's always going to happen. Switching gears a little bit, we had a lot of experience working with the hospitality industry and have evolved very good partnership relationships with management at a wide variety of different hotels. And hotels are really unique environments because they're very energy intensive and they're very much driven by user preference and demand. People are very hard to please in these types of environments. So it's a very unique test site for us because we learn a lot quickly and easily. And this is a chance for us to take new technology and move it into the marketplace. And we have a lot of experience and a lot of data going into hotels and actually measuring where energy is used and where it's not. And we've done a lot of monitoring, and we've gone in and we've monitored all the lamps and side spaces, trying to understand where energy is actually used. This is actually a small monitoring device that's been glued onto the side of a lamp, and we put them in there and we leave. And then 6 months later, we take this and we download the data and we look at the dynamics there. We actually have to mark this that, please don't remove this equipment. And sometimes the management gets calls that the room is being bugged, so we have all kinds of issues with that. Sometimes we come in, there's no monitor, it's gone. Sometimes the whole lamp is gone. We did a hotel up in Sacramento where they did a large deployment of Berkeley lamps, and we got a call from the manager of the hotel, and he says, Michael, we have a really big problem. And I said, oh my God, there's a fire or something with our technology, And he says, 2 of the lamps disappeared last night. And I go, oh, all right. And it was sort of like the classic mark, if someone's willing to steal it, it must be okay, He wasn't amused. So anyway, lots of monitoring of inside rooms. This is a relatively busy graph. I want you to only look at one array. And that's this array here. And what we're showing here is, this is time of day here, and this is just the probability that a light will be on, okay, at a particular time of day, boiled over a large series of rooms. This is the bathroom, and I'm only going to talk about bathroom lighting. It turns out that's where all the interesting stuff is happening. So what we're showing here is that the classic increase in usage towards the morning, okay, and then it peaks out, in the morning. That's when hotels' bathrooms are classically being used. And then we expect a decay, and we get less and less and less use. But what was real interesting here was that we peaked out here and it flattened. It stopped at 2 p.m. and it stayed fairly high all afternoon, where we normally would expect a very big dip in this and then back up again towards the evening. It didn't. It stayed on. And at this point in time, we said there's some really interesting things going on in here, and we decided to take this a little bit further. This is a histogram of usage in a bathroom, okay? And this is fairly standard. If you go back and work with the hotel folks, most of the folks know that this kind of dynamic exists. And I want to walk through this a little bit. This is showing essentially the very peak usage is about a minute. This is essentially going into the bathroom and washing your hands or grabbing a tissue or whatever, 1 minute. And then it peaks down to about 4 minutes. And then there's another peak at about 16 minutes. This is taking a shower, brushing your teeth, whatever. Okay? So there's a peak there. And then it decays down, to 30 minutes, an hour, 2 hours. That's a long time, and then 4 hours and 8 hours. Now remember, this is the lights are on. They're not necessarily there. We have data on people being in the bathroom this long, but this is just lights, okay? The lights are on. We don't know whether there's anybody in there at 8 hours. There could be. But what's real interesting here is that this dynamic is well understood. And this dynamic for lights is probably what's happening in everybody's home, in every dorm, in every kind of home. This kind of double hump dynamic exists. What we found was real interesting was that this is the stuff we normally design for. We think about this kind of stuff. It's like the 1 minute usage and the 16 minute usage. That's the important stuff. That's when we know people are there. what gets interesting, if you take this data, which is strictly time, okay, and you convert that to energy, okay, you get this function. So this is the same data that you just saw, but now converting it to energy, and that's what we're all interested in. And as it turns out, all the stuff where you see the heavy usage is insignificant. Okay, that's down in the noise. What's really juicy out here is the lamps that are on 2 hours and longer. That's where the real action is. And what's interesting here is that stuff rarely ever happens. Okay, you can see this is the probability of on. The lamp being on for 8 hours doesn't happen very often. But when it does, it's really meaningful in terms of energy. Now, what does this all mean? What it means is that occupancy sensors could save an enormous amount of power savings in bathrooms and hotels. Hotels will not use occupancy sensors in bathrooms. And there's an unwritten rule, and unless you go drinking with these guys, they won't tell you this stuff. But what they tell you is that, Michael, we will never use occupancy sensors in bathrooms because if the light goes off and someone's in the bathtub or whatever, all hell breaks loose. And and full points to them. I mean, if a person is spending $200 a night and their light goes off, you can be sure the management's going to hear about that. So we worked very closely with our partners in the industry on this. And we went back to them and said, we studied this in detail. And what we found was that the significant stuff is all happening out here at 2 hours and longer. So we had a proposal, and the proposal that we made to our partners, and this is the hotel industry at a fairly senior level, we said, we can develop an occupancy sensor that has a 1 hour set time. And it will become institutionally transparent to anybody that's in the bathroom. In other words, if a person's concerned about a light being turned off after an hour, they've got some other issues, okay? And the idea with an occupancy sensors typically are 15 minutes. The occupancy sensors that we have all around the laboratory are in very short set times. Now, with a 1 hour set time, an occupancy sensor, if it sees anything within that hour, it will reset itself for another hour. So the hotels at this point in time said, this is really juicy. We really want to work with you because an occupancy sensor with 1 hour set time will be totally transparent. So what we developed was this technology here, and we actually brought one of the units here. This is essentially a wall switch. I want to sort of, and this just, normal wall switch. And buried into this is a dual technology occupancy sensor. And the technology here also has a twin LED, amber LED built into it for a night light. Now, it turns out that there's lots of folks that turn on the bathroom light in a hotel and close the door a crack so that when they need to get up in the middle of the night, take a whiz, they can see their way to the bathroom, okay? And so what we did is we built in this integrated night light with the idea that, I'm just going to go back here real quick. This stuff here, what's this light on at 15%? What this means is that 15% of all hotel rooms at night, the light is on. Now, the light is on there because someone wants to be able to do what they do in the light, okay? And so that's a nightlight effect. We thought it was going to be much juicier, but it's not. It's about a 15% effect. But what we did is we bundled the technology and we built a nightlight into this to essentially erase this 15% that occurs at night. The positive feature on this is that in the middle of the night, you're in a hotel room, you get up, you go to the bathroom, the lights are on. When you essentially bleach out the rhodopsin in your eyes, so now you have no night vision. So when you head back to the bed, any positive effect you've had from being able to see in the bathroom, you've lost because now you're tripping over everything that's in your room because you can't see anything, okay? So the idea with this is there's enough flux coming out of this for you to do this. And we did a series of initial studies with this, and we actually had the director of engineering for a large hotel company and their CEO and myself with this technology in a bathroom. And I closed the door and I turned off the lights. Needless to say, they were somewhat nervous. But what happened was I said, dark adaptation takes about 15 minutes. There's 2 steps in dark adaptation. And after a few minutes, the CEO was going, hey, I can see everything in here. And it's true. Your eye adapts. But there's not enough flux there for you to lose your night vision. So this was a real big feature for him. What was the second big feature was the idea that they were going to capture 75% potentially of the savings, and they were going to do it in an institutionally transparent manner. Guests will never know their lights because they're at the beach. Okay? So what we did was we formed a partnership with Sacramento Municipal Utility District, with the regional director of the Hilton, and with Wattstopper, the company that built this. I'll actually show you how this works. Turn this on, brush your teeth, split to the beach. Okay? Forgot to turn the lights off. Okay? The light will turn off after an hour automatically, or you can turn it off yourself if you're so. And on comes the night light. So that's how the technology works. It's very, very simple, very straightforward, really easy to install. Just snaps in. So what we did with this partnership is we went in and we relit the entire facility. It was 400 plus rooms in Sacramento at their main business flagship property where we put this technology in. And we did a lot of measurement verification work, lots of monitoring, really trying to understand what the savings and what the potentials are. This is a little bit lots here on one graph, but essentially this is that energy graph that I showed you earlier where all the energy is happening out here. And what we're showing here are bundles of time. This is lamps that were typically on for 10 hours, 5 hours, 2 hours, 1 hour, etc. What this sensor is doing with this data set is we're completely eliminating the 10 hours, okay? That virtually. On this one, this is a before and after. We still have some usage of 5 hours. Now what this says is that people are indeed using the bathroom for lights for 5 hours, okay? Now it could either be 5 single trips into the bathroom triggering this, or someone sitting in the bathtub for 5 hours. It's either or. We actually have some of that data, but we didn't want to share it with you. And this is showing again is that what we're doing is we're eliminating the large usage on this, and that's really where the fat is on this process. This is a boiled data in which what we're doing is showing the daily dynamic over a large series of rooms for many, many days. Okay? And again, it's the same function I showed you earlier, in which the blue shows a typical day, in which this stuff here, that's nightlight. This is like in the middle of the night. This is nightlight. This is people leaving. At this hotel, it was about 7% of the people were using the bathroom light as a nightlight. Okay? And then showing very heavy morning usage, and then it decays down. And then you see this sort of heavy, not heavy usage, but sustained usage in the afternoon. After, you can see we virtually eliminated the nightlight phenomenon. People are using this as a nightlight, which is nice because we were able to show that was working. But there are two big opportunities here. One is, this is a business property, so most of these guys are splitting after they do whatever, they leave. And what we're showing here is that this is a fairly juicy savings, and all the people that are splitting in the morning that are leaving their lights on, in other words, they're so busy they leave the bathroom light, they're gone, okay? We're capturing that. This phenomena here is both the business person leaving the lights on, but also the cleaning people. I mean, the cleaning folks come through, they do whatever, sometimes they don't turn off the lights. Okay, so that's what that effect is. We get a secondary effect here in the evening, and this is, they're coming home now, so we don't get as much difference. They're, changing into whatever, and then they're leaving. Now we're getting the after dinner response, okay, which the person's left the light on, it's on all evening. We're getting a pretty juicy savings there. What we're real interested in is peak power. And peak power is traditionally, all afternoon into the early evenings. And we're getting, 40, 50% effects here at peak power. So this is a real juicy opportunity for peak power savings. What's next for us? We're working really closely now with the second wave on this with the utility folks. And the utilities are really interested in this because it's kind of a slam dunk. It's kind of a no-brainer. but it involved some real critical market transformation barriers where the hotel said, no, we're not ever going to think about doing that because it'll tick off our customers. Now they're into it because they know that will never happen. So we're doing more deployments on this. We're also looking at other applications. Our thesis, and we haven't proved this out yet, is that dorms be a big application for this. Residential applications, we're meeting with SMUD on Friday to talk about doing a residential program on this. Military housing, we're going out to Honolulu to do some more studies. And military barracks, big opportunities there. Ron, do I have a few more minutes?
Yeah.
I've got 300 slides, so. We got real involved with doing lots of residential work, as you can see. And one of the real rich areas has been exterior lighting. And as mundane as it sounds, porch lights are a real juicy opportunity in this country. And it's juicy because, one, porch lights traditionally use incandescent sources. And they're on for long periods of time.
24 hours a day?
Sometimes they're on all night long. You know, I have a neighbor, and she leaves all her lights on, you know, and it's on all the time. So it's a really interesting opportunity. And what's also real interesting about it is that there's areas that we can apply in our optics research and some of our advanced source technology where we can have a really big impact. If you took a very typical porch light geometry and you looked at its optical distribution characteristics, you get this type of bipolar distribution. And what's really significant about this bipolar distribution is that this sends light just about everywhere you don't want it. You know, so ultimately, it's not just the efficacy of the light source, but is how effective is a light source at creating light where you might need it. Okay? This bipolar distribution is sending light all over the place, but not along the wall here where you might want face recognition to see, you know, who's coming to my door. Also, sign recognition if you've got a number up here. Also, folks that want to see whether there's a cat or a dog or ice or whatever on the ground. So this is very important. This is a lot of the work that we do is trying to optimize the distribution characteristics on this. And we can get great amounts of efficiency because I could take this fixture here, forget about the efficacy of it, of the light of the actual source. I could hack that off and turn this around and put all the light down there, and I'd have a much better system at half the power. So that's the kind of thinking that we're doing. We're doing is we're teaming up looking at LEDs, light-emitting diodes, as a source technology for this system. And we've developed this. This is the prototype of it here. This is a porch light. And the idea of this porch light is that it projects all the light downwards. Okay? And this is exactly where you want it. You want it along the face of the building. Okay? And this is it's got an LED amber array along here. Okay? And this array here matches the performance of a 60-watt bipolar system. And the idea here is that this system produces high levels of light where you want it, along the face and along the stairs. And it also does it with a technology that will last for a very, very long time. So the idea is that we're also working with the dark sky folks. The dark sky folks are the ones that don't want a lot of light pollution. So if you're in any major city, you can't see the stars anymore at night. And the reason is all the night pollution. Light from porch lights are going up in the sky, scattering, and it's creating a veiling component so that you can't see the light from the stars. One of the efforts that's being looked at now by lots of communities is to look at light fixture ordinances which will restrict the amount of flux that you can project into the night sky. Secondary effect is energy efficiency, and we think that this is going to be a real opportunity for us. We're looking at lots of different, it doesn't have to be something that is, this is a little bit out there, but we're actually looking at integrating this in with fairly conventional, if you want to have the colonial style porch light, with the whatever, we're looking at taking this system and integrating it into the actual hardware of fairly traditional light fixtures where we're starting to approach comparable performance at about 5 watts. So a 5-watt system will match the performance of a typical commercially available porch light, which is a really big savings for us. I'm going to stop it there. I'll save the other 250 slides. Questions?
A couple of questions. First, what advances are we making in the area of parking lot lighting?
Yeah.
And then secondly, what input did Berkeley Lab have in the development of the phosphor material in the lamp? Thanks.
I'll take the last question first. Sam Berman, who was the director of the lighting systems group, who started the lighting systems group, was real involved with a lot of the phosphor research. And I know that one of his early proposals was on both the isotope work with the phosphorus and also the twin photon phosphor work. And to the best of my knowledge, that work, there's one portion of it that's going on elsewhere. Sylvania had worked a lot on the isotope work, and I'm not sure where that all went. I know that some of the early results that I saw, there were fairly small gains in efficiency, even though there was pretty large, projected gains in it. But the work that they did on the isotope, they didn't show large gains in it. I can talk to you a little bit later and give you some references on that, or follow-ups on that. But that's not an area that we've either continued or didn't show much promise when I first saw that. I can direct you to Sam Berman. I know that he's been keeping his hand in that at some level. On the first one on parking lots, a huge opportunity on parking lots, but it's a thicket of thorns because if you fly into any major airport at night, you go over parking lots that are illuminated as far as your eye can see, and there isn't a person or a car there, and it just gets you crazy. Particularly going into Chicago after a snowstorm, and it's so white and bright, and yet it's so well lit, and there's not a car in the place. And Southern California Edison is looking very hard at both improved optics to reduce the sky brightness, but also occupancy sensor-based systems where it goes to a high-low function. It's really a problem. We had a fairly major proposal on this. The problem is one of liability. And you go out, to a car, and your car is, at the far end of the parking lot, and you're the only person, and that car's over there, and it's dark. And it's a bi-level system, or it's off, or there's an occupancy sensor. Occupancy sensor system doesn't work quite right. You got a major poo-poo. It's a major problem. And people are scared about this. I think it's going to involve some really major thinking about rethinking about how do we integrate new technologies and do it in a seamless fashion. It's a huge opportunity. The other problem with this, a lot of the stuff is off-peak. So the utilities, while interested, are not. So if you could figure out the Trojan horse for that liability issue, we were arguing that an occupancy sensor system could enhance security because if you're walking and all the lights are on, there's either a problem or you're safe. Now that's kind of a, you know what I mean? It's problematic. More questions?
Yeah, on the Torchiere, I still have my halogen one at home, and the main reason is
Shame
there's
on you.
any dimming capability. I really like the whole
Sure.
range of light that comes
Yeah.
out of the halogen.
Yeah.
It's really nice. Now, you can do it on the Berkeley Lamp. Are they doing it on the Torchieres now?
Yeah, actually, and that's a real issue. And this technology does dim, but it's not a continuous dim. It goes to about 50%. Okay, and we found that in the studies that we did on the Berkeley Lamp that the 50% dimming function was enough for most folks. It's not going to give you that 5% light that a lot of folks like to see on that. And it's very true. This can dim down to 5%. It's feasible technically to get a ballast, this thing here, to do that. It's just that it changes it from a $10 ballast to a $20 ballast. And the company's made a strategic decision, and not by me, but they made it, we won't do that. And there's enough of a marketplace to sustain that. There's just enough of it there to do that. And eventually you'll be able to do it, but not today.
It seems that one of your big successes is getting partnerships, both on the utility end and with companies to do the building of the lamps and with companies to be test beds. How do you go about doing that, you also get very high visibility as a result, and therefore a larger acceptance because you get a lot of newspaper and news quotes, and that seems to be a real forte of your work. How have you been
Well, it's a
doing that?
chicken and egg. I mean, when we first started doing this, we said, well, we'd like to work with industry. What? You got to be kidding, Yeah, a national lab, work with a manufacturer. Why would you want to even think? You're supposed to write scholarly papers. So I did the scholarly paper deal, and that was good for a while, but it just didn't, for me, for our group, it's much more exciting commercializing stuff and getting stuff into the marketplace. And while I don't say no to scholarly papers, I haven't written a scholarly paper in years. And, my boss doesn't like that, but that. The issue with the partnerships was that we learned that with the first series of commercializations that we were able to get this stuff quickly into the marketplace, and because we didn't have all the tools. And we needed to have partners both who could make the toys and use the toys in order for us to evolve them. In other words, we didn't have enough information to be synthetic in the laboratory. So we valued from that relationship with a manufacturer we worked with. He said, no, you don't know the first thing about this. You need to do it this way and this way. And that helped us accelerate that. So initially, by doing that a few times, that proved to us that was effective. And so we sought that kind of partnership effort out a lot. The technology transfer people were very effective on this. And their mantra is to work with partnerships and to work collectively with the industry. So we've teamed very closely with the tech transfer people. And that's been a very effective relationship. But I think it's a chicken and egg issue. Is that once we started doing it, it started feeding itself. And that when we go to a manufacturer or we make broadly available and said, look, we'd like to form a partnership and we'd like to commercialize something, they're interested right away. And we say, oh, by the way, we've done all these things, and that gets their interest. Do you want to, please?
Yeah, a follow-up on that. Is DOE very supportive of that? I know that it's gone through periods where, industry should be doing their work, we're not supposed to be doing the work for them, and then back and forth, and tech transfer and no, and...
I mean, it's sort of like, those things that come and go, and sometimes it's, we are going to take a basic science view of life, and you and I have seen that a number of times, and it's like, you're all measured by how basic your research is, and that any work with industry is like, Jesus, why are we doing that? And I think you need to have a balance. You need to have both. You need to be folks doing basic science work, and you need to have folks that don't mind working with utilities and working with industry. You need to have both. And a healthy research palette has to have a wide scope. It just seems that in my opinion, is that it's always the tech transfer or the partnership or the industry work that gets sort of shot at first. And I think that comes and go. We have, our value is sort of self-evident, and we survive because we get results. And it's available online. You can go to either our website or LightCorp and order it there. We had envisioned a much larger program in the last year with utilities and with other folks. But because we've been suffering the last year on the ballast failures on this, and it's just been reintroduced this month, we've been slow on developing the rebate programs and the other programs. So I would give it a little bit of time, but the technology is available. If you do indeed want one, go to their website and you can order one there. And it's 100 and something, I mean, in that range. I mean, it's like between 100 and 200. I know it's not. These kinds of technologies are always, we're looking to do utility programs as the next step, and we've just gotten through the first sort of real problem on this, and we don't expect any more problems. So go to their website. If you have any problems, come see me or look at our website.
Join me in thanking Michael